Hello and welcome to my Mech 3027 assignment. My name is Damon Cooper. Here you can see a list of all the features I've achieved, so pause now if you want to get an idea of what my car can do. And here is just a basic schematic diagram of the vehicle. I will begin by giving an overview of the Tinkercad circuitry. So here you can see I've got 3 ultrasonic sensors, one at the front of the car and one on either side. I have a magnetometer represented by a potentiometer, and this outputs the heading in degrees. I have a switch to represent the bumper at the front of the car, a DC motor powered by 2 9-volt batteries, a camera module represented by 3 switches, servos for the left and right wheels separately, an ambient light sensor, and finally 2 LEDs for the headlights. Moving on to my code, this is the code for my magnetometer slave. So what this does is it reads the potentiometer position and converts that to a degrees value for heading. So as you can see, as I'm changing the potentiometer, the value for heading is changing, and then it then sends that value to the master Arduino. In my camera slave, the cameras are represented by these 3 buttons, and each of these buttons corresponds to a turn and a degree of bend. So this first button represents an easy bend. If this is pressed, you can see that the serial monitor is printing easy bend approaching, and the out value for bend would change to 66, and then that value would then be sent to the master Arduino. Apologies, I was just watching the exported video just to check for any mistakes, and I realized these comments were in the wrong place. So what you're seeing now on my screen is the correct position of the comments, so just like labeling all the out values. But in the rest of my footage, whenever I show these comments, they're in the wrong place, so here is where they should be. This is the code for my master Arduino. So here I've just included my libraries, and this is me defining my pins and variables. Here I've just called the functions to read the slave Arduinos, and the code for that is at the end. So you'll see that in a minute. Here I've set the servo angles. Here the ASCII inputs are mapped according to where they lie on the alphabet. So values between 65 and 90 are used for the motor, etc. This is the code for my light sensor. So if it's very bright, then the LEDs will turn off, and if it's very dark, they will turn on. And this delay here is just to prevent flickering. Here I've activated my ultrasonic sensors. This is the code to control the motor according to rec speed. Here the input sensor values are mapped to ASCII and then printed out into the serial monitor. And here is the code to read the values from my slave Arduinos. This is my LabVIEW block diagram. So as you can see, the 8 output values from the master Arduino are taken and put through various functions. So here you can see the ultrasonic, heading, and camera values are the inputs for the steering and the speed fuzzies. In addition to that, up here we just have some code where these lights turn on if there is nothing in range of the ultrasonic sensors to trigger them. This is the code for my headlights. So if the light flag is activated, then a little light will come on in the user display just to indicate that the headlights have turned on. And then the light level is also sent to a meter. Whether the car is in automatic mode is dictated by this switch. So if the switch is on, and then this case structure is true, and the speed and steering fuzzies control the output for steering and speed. And if the switch is off, then this case structure would be false. And you can see these 2 manual controls, which are just dials, dictate the steering and speed output. So here the speed percentage is converted into a string. And this here, while it might look a little bit complicated, is just the Ackermann steering formula for a car of wheelbase 20 centimeters and lateral wheel separation of 10 centimeters. So that's these 2 constants here. And what it does is it takes a steering angle and then converts that into an angle for the right servo and the left servo. And that is then converted into ASCII string. I will now demonstrate the manual control of my car. So as you can see, this light is not on, just to show that automatic mode is not engaged. And if I change the speed dial, then you can see the speed gauge is changing accordingly. And if I change the manual steering angle, then the steering angle meter shows the direction the car will turn in, and then the the 2 meters below that show how far the right and left servos would turn. So if we're turning left, then the left tire would be the inner tire and would turn at a greater angle, and the right tire would be the outer tire and turn at a lesser angle, according to the Ackermann steering principle. To demonstrate the automatic control of my car, I'm just going to come back into my Arduino briefly so I can play around with the sensors, change the sensor values, and that will then give me a string which I can plug back into the LabVIEW. So let's say there's a very distant object on the front and left sensors, and let's say there's a very close object on the right sensor of about 20 centimeters. We'll say it's dark, so the lights have been activated. We will say the car hasn't crashed and none of the camera buttons have been activated, and we'll say we're going on a heading of about northeast. So that gives me an output string of STBABAAP. This here is my steering fuzzy. So as you can see, the values of distance range from 0 to 350 centimeters, because that is the range of an ultrasonic sensor. Same for the right, and this is my heading input. And here are my rules. And just briefly, you can see there is a linear relationship between the left and right sensor. This is my speed fuzzy, so if there is a close object on the left or right sensors, the car will slow down. And this is my degree of bend input. I didn't bother to make this symmetrical just because these values are only ever 0, 1, 2, or 3, and there's no overlap, so it works perfectly fine. These are my rules, and this is the test system. Now that I've shown you my fuzzies, just so you can understand how this is about to work. So if we go back to that string that I produced earlier in my master Arduino, STBABAAP, and if I enter that string and then activate automatic mode, you can see that we are turning left as is to be expected. We're going pretty quickly and the headlights are on, and it has produced this string. I'm now back in my Arduino, so if I enter the string that was produced by the LabVIEW, which was an uppercase S, a lowercase p, and a 0, if I just enter that string, then you can see that the RPM of the motor has been set to the desired value and the servos are in the positions that I wanted. I will now run through my code for the bumper slave Arduino and just what would happen in the event of a crash. So the reason I have a slave Arduino for my bumper in the first place is because I wanted there to be a timed action. I tried doing this using millis, it didn't work, so the next best thing was just having a delay of several seconds. Obviously, I can't have a delay of several seconds in my master code because then I just wouldn't be doing anything for quite a long time. So a slave Arduino solves this problem. The motivation for this timed action is that when the car hits something, the bumper won't stay depressed. So maintaining the out value for a few seconds gives the car time to take the necessary action. So if the car hasn't crashed and this button hasn't been pressed, then out value 7, which is just the second last letter here, will be a 65. But if it has been pressed, i.e. the car has crashed, then out value 7 will be 66 for 2 seconds before reverting back to 65. So yeah, there you go. You can see it's changed. Here in my lab, you can see the code in the case of a crash. So if the value is greater than 65, an indicator would come on to say that it's crashed. And this here is the condition for the case structure. So if it's 65, then the car hasn't crashed and all this is activated. But if it has crashed, i.e. the case structure is false, then the steering angle is set to 0 and the speed is set to -20. I'll now just demonstrate it in the front panel as well. So if I change this to a B, there, You can see that the values have been set accordingly. Going back to my camera module for just a minute. So these buttons represent a camera recognizing a 1, a 2, or 3, which corresponds to a bend sharpness, but in reality, this will be hooked up to a real camera with a neural network. So this is an example of a neural network. It has been trained to recognize numbers. So here is a 1 that I drew. And if I plug that into the neural network, it recognizes it as a 1. The motor controller I've used in my assignment is a simple open loop program, but in most industrial and commercial applications, closed loop control is used, a very common form of which is proportional integral derivative or PID control. Here you can see an example of a DC motor utilizing a PID controller, and we are able to more accurately and safely control the motor speed.
In summary, I have successfully built an autonomous vehicle with working sensors for the light detection, object proximity, heading, turn sign recognition, and collision detection. The vehicle direction and speed are operated either by manual control or fuzzy controllers through a LabVIEW interface, which are then put into action by a DC motor and servos operated according to the Ackermann steering principle. The code and wiring are organised as neatly as possible in order to make it easy to read and understand, and there are comments throughout the code. Collision procedures are controlled by case structures, and the LEDs do not flicker if they are triggered very briefly. I am now at the end of my presentation. Thank you for watching and Merry Christmas.